To grasp the energy band structure and the energy band gap, one simple problem. There is one simple problem, and it is well on the Kronig Penney model. In quantum mechanics, we know that there is a famous problem for the quantum well and quantum barrier, and energy barrier. Then, Kronig-Penney model is a periodic potential, one-dimensional periodic potential, for example. And here, this is energy. It is a potential, Vx, and it is x. It is one-dimensional. Then let's assume that the potential height is a V0 and the potential width is B, and the potential distance is A, like this. It is A and A plus B. Like this. Minus A minus B, like this. And there are then this potential is periodic, and there are three regions. One is that region 1 and the region 2 and region 3. Here it is a one-dimensional periodic potential. It is a V0 is a potential height, and B is the potential width, and A is that spacing of potential, spacing between two potentials. And the Kronig Penney model can be solved in, it is a real space. It is a real space potential. Then there are two methods to solve this Kronig Penney model. One is that, one is that the real space Schrödinger equation. The other one is that the momentum space central equation. And the momentum space central equation is identical with the real space Schrödinger equation. And let's in this at this point, and let's think about that Schrödinger equation in real space. And in one-dimensional Schrödinger equation, and h bar square over 2m d square psi dx square plus potential psi equal to epsilon psi. It is a Schrödinger equation. In region 1, there is no potential. There is no potential, and the potential equal to 0. And we know that the solution of this wave function, and here the detailed calculation of this potential well and potential height can be studied in the quantum mechanics. I assume that you already know that the result of quantum mechanics. And here the solution of this in region 1 is that a exponential I kx plus b exponential minus I kx. Here is the wave vector of k is representative that here h bar square k square over 2m. Here because region 1 there is no potential, and it is a free particle. Energy is kinetic energy. And here region 2 is that potential. There is a potential well, potential height, in region 2, potential equal to potential V0. Here, we know that there is a dissipation of the wave function. Therefore, the solution, general solution in region 2 is that the dissipation for exponential qx plus d exponential minus qx. And because, as you know, then the c equal to 0 because it is a dissipation, not the divergence. And but in general, and the qx and minus qx, the combination, the linear combination is a general solution. And here, the energy, because we assume that the potential energy is lower than the potential because and the energy is higher than the potential energy, and it is like a free particles. And here, this dissipation is occurred, and energy is lower than the potential energy. In this case, h bar square. Let's assume that it is q square. Q is that the wave number in this potential barrier. And in region 3, region 3 is a periodic potential of the region 2. Therefore, here we apply the Bloch theorem with potential in this 3 is that periodic lattices. And therefore, here we apply that the Bloch theorem with periodic region of 2. And therefore, in region 3, potential wave function is that the Bloch function of the wave function of in region 2. Here exponential ik, and the distance is a plus b. And here the distance is the a plus b, and therefore it is a Bloch wave function. Here there are three regions, and in 3 regions we have the different wave function, and but there should have we consider boundary condition. And the first boundary condition at x equal to 0, and the wave function should be continuous and smoothly continuous. And therefore, the continuous condition and one wave function x equal to 0 should satisfy that region 2 wave function at the 0. Therefore, from equation 1 and 2 and 3, and from equation 1 and 2 at x equal to 0, and the solution is that a plus b equal to c plus d. Let's think that it is one plane. And this wave function should be continuous, smoothly continuous, and it means that d psi 1 dx at the x equal to 0 should equal to d psi 2 dx at x equal to 0. Therefore, then when differentiate with x here ik, and at x equal to 0, a minus b, then equal to in the dx in region 2 in the q c minus d, and it is 2 prime. And the other condition is x equal to a, the wave function between the region 1 and region 3. Therefore, at x equal to a, there should have the psi 1 at x equal to a should satisfy the psi 3 at x equal to a. In x equal to a case, and a exponential ika plus b exponential minus ika should have the in x equal to a in region 3, c exponential minus qb in 3, yeah, in because in here in region 3 we apply this one, and if psi 2x at x equal to a, at x equal to a, and x equal to a is that the periodic lattice with the x equal to minus b. Yeah. Here we assume we supply that it is psi 3 at x equal to a is that psi 2 at x equal to minus b, and exponential ik a plus b. Here we applied from the 3 condition, and here at x equal to a is that from the periodic lattice, and equal to x equal to minus b in second region. Therefore we apply this one, and here therefore, and in x equal to minus b, and from equation 2, see equation exponential minus qb plus d exponential qb, and exponential ik a plus b, and it is third equation. And also it should have the equation should be continuous and smoothly continuous at d psi 1 dx at x equal to a should have the d psi 3 dx at x equal to a. Then in this case, and it is identical, psi 2 dx at x equal to minus b, and exponential ik a plus b, because it is third condition, and it is wave function 3 is the wave function b, and it is at minus b, and and it is minus a plus b periodic. Therefore, and here d psi 1 dx is that ik exponential a exponential ika minus b exponential minus ika, and also this one is the q c exponential minus qb minus d exponential qb, and exponential ik a plus b. It is a fourth equation. From the 1, 2, 3, 4 prime equation, and there are the coefficient, the unknown coefficient is ABCD. ABCD is unknown coefficient, and there is a coefficient. And therefore, then let's think about that. We can make the matrix in the ABCD. Therefore, let's make the matrix. And A case 1, 2, 3, 4. Let's say that 1 ik, and third exponential ika in the fourth, ik exponential ika. It is A. And B is that it is 1 and 2 minus ik, 3 exponential minus ika, and the fourth minus ik exponential minus ika. In the C, minus 1 is minus 1, in the 2 it is that minus q, in the 3 minus exponential minus qb exponential ik a plus b, and also c minus q exponential minus qb exponential ik a plus b, and also finally in the 1 is that minus 1, and 2 is that q, and the third one is that minus exponential qb exponential ik a plus b, and the fourth one is that q exponential qb exponential ik a plus b, and also the matrix a, b, c, d should equal to 0. It is in order to have the non-trivial solution of this A, B, C, D, when we make this is a matrix M, and the determinant of matrix M should have the 0 to have the non-trivial solution. The determinant of this matrix M is very complicated to calculate, and therefore it is necessary to write the final result. The final result of this determinant M equal to 0 is that q square minus k square over 2qk and hyperbolic sine qb and sine ka plus hyperbolic cosine qb cosine ka equal to cosine ka plus b. It is a final result. And here it is a result of the Kronig Penney model. And anyway, and in order to have understand more simply, and let's consider for the delta function of potential. Consider delta functional potential. Then delta functional potential is that the potential width becomes 0 and the potential height becomes infinite. In this case, because in the q and k, and it is energy and the q like this from this one, and because v0 is very high, it becomes infinity, and the q is very high. And also here b is very small. B is very small. Therefore, here q is very high comparing with k, and QB is very small. And therefore, from this assumption, and we should think about that. Here is this one, and cosine hyperbolic, and the sine hyperbolic QB is that exponential QB minus exponential minus QB, because it is very small QB, and it is close to the 1 plus QB and minus 1 plus QB. Therefore, it is QB. And also, hyperbolic cosine QB is that exponential QB plus exponential minus QB. Therefore, it is 1/2 1 plus QB plus 1 minus QB. Therefore, it is equal to 1. Therefore, when we substitute this, the result of Kronig Penney model, then q square minus k square over 2qk, and sine hyperbolic becomes QB sine ka, and plus cosine hyperbolic QB is 1, and cosine ka equal to cosine Ka, because b equal to 0. And because capital Q is very high comparing with capital K, and it can be write down as that Q cancel with each other, and 2K and Q square B sine Ka plus cosine Ka equal to cosine Ka. Here let here this one we call it as alpha. Not this one, in the alpha, because here here cosine Ka Ka, therefore let's make Ka. Let's define that alpha is that Q square over 2AB. Then it can be write down as that Ka over alpha over Ka sine Ka plus cosine Ka equal to cosine small Ka. Therefore, let's define that the right side is any function of Ka, is a function of Ka, and the right side is the small k cosine Ka. It should have the plus minus 1. The absolute value should include the plus minus 1. For this one, the absolute value of the Fk should within the plus minus 1. Therefore, the solution of this model is that here the Fka is that like this functional form and the oscillation, but cosine small Ka within the cosine Ka within the plus minus 1, therefore it should reside in the plus minus 1. Therefore, this shaded region is unprohibited region, and also therefore in this case we also consider that the allowed case is that the function within the plus minus 1. Therefore in the x-axis and this black line is that only allowed region, and therefore the Ka is there is only allowed region. Therefore we should only consider it there are two regions, prohibited region and allowed region, and that's why the prohibited region is the cause it causes the energy band gap. Here it is energy band dispersion, and this energy band dispersion between the x-axis is k and y is the energy, and therefore the allowed k value only have this region, and we plotted this from this equation, and from the Kronig Penney model there is the prohibited region and the allowed region. We know that the left side is extended Jones scheme, but because there is a periodic lattice, and we can the 2 pi n shift by 2 pi n is identical because of the periodic lattice. Therefore this energy band can be shifted to the 2 pi, and therefore in this case then the reduced right hand side is the reduced Jones scheme within the first Brillouin zone, and therefore we can say that there is the energy band gap in here, and a continuous band dispersion, and there is energy band gap region, the unprohibited region. Therefore it is a solution of the one-dimensional periodic lattice, and the cause of this periodic lattice makes the energy band gap.